In this overview video, I would like to discuss the formula for the Laplace transform of e to the at times f of t and the corresponding common examples. So the formula is quite straightforward. The Laplace transform of e to the at f of t results in a shift of the Laplace transform of little f. And oftentimes it may be convenient to rewrite this as big F of s, and then just note that s becomes an s minus a. So for example, if we wanted to evaluate the Laplace transform of e to the t cosine of 2t, our a value is 1. So this will be the Laplace transform of cosine of 2t, where we make the s become an s minus a, so s minus 1. The Laplace transform of cosine of 2t is s over s squared plus 4, and every s needs to become an s minus 1. And we have the desired Laplace transform. And we can do the same thing with many other choices for a function f. So for example, here we have a equals minus 2 and little f being t cubed. So this would be the Laplace transform of t cubed, where the s is going to become an s minus a minus, so that would be an s plus 2. The Laplace transform of t cubed is 3 factorial over s to the 4th. And if we make that s an s plus 2, we have the desired Laplace transform. We can also investigate similar problems using the inverse Laplace transform. When we see an inverse transform of an f of s minus a, so there's kind of that composition, that would remind us to use this formula. And an equivalent way of writing this would be that the inverse transform of big F of s minus a is e to the at times the Laplace transform of that big F without that shift. So a few very common examples. Note that s plus 2 raised to the 5th power is of this form s minus a minus 2. So our a value is minus 2. So this would be e to the minus 2t times the inverse transform of the function without the shift. So that would be 3 over s to the 5th power. Now what remains is just a familiar problem. So our n value here is 1 less than 5, so it's 1. And the number we need in the top is 4 factorial. So if I want a 4 factorial in the top, we could simply pull out the 3 and put a 4 factorial in the top. But of course that's not something that we can do for free. If we put a 4 factorial in the top, we need to balance this off by dividing by a 4 factorial out front. So that would give us an e to the minus 2t times 1 over 8, and then that inverse Laplace transform is precisely t to the 4th. And then one more additional example where this comes up quite frequently is when you have a quadratic that doesn't have 2 real roots. Instead, how we can approach this is by completing the square. Note in this case, this doesn't factor nicely into 2 linear terms. If it did, we would complete the square and we would get an inverse transform involving 2 exponentials. Instead, what I'm going to observe is if I look at this s squared plus 4s, that would really be the first 2 terms of s plus 2 quantity squared. But note, s plus 2 quantity squared would be s squared plus 4s plus 4. We have a plus 13, so I need another 9 to go with that 4. And I think working our way through it intuitively is almost always the best approach here. So we have the inverse transform, 1 in the top, and in the bottom we have s plus 2 squared plus 9. And we now compare to this formula that we have above. This looks very similar to the sine of 3t formula, but we have this shift here, s plus 2 again. So in this case, our a value is equal to minus 2. So we can write this as e to the minus 2t, the inverse transform of 1 over s squared plus 9. Now that we have it in this form, if we put a 3 in the top and divide by a 3 out front to balance it, we're left precisely with that inverse transform formula for sine. So we would have a 1/3 e to the minus 2t sine of 3t.